Let's try problem 6.14. The radius of the Earth's nearly circular orbit around the Sun is 1.5 times 10 to the 11th meters. Find the magnitude of the Earth's velocity, angular velocity, and centripetal acceleration as it travels around the Sun. Assume a year of 365 days. Okay, so the first thing we want to do is find the velocity of the Sun of the Earth as it travels around the Sun. So part A. So we learned in the first couple chapters that distance is equal to velocity times time, or velocity is equal to distance over time. And so this is kind of like the same type of deal right here. So we have the Sun in the middle, and then we have the Earth, and that's a perfect sphere, rotating around it. So let's say that's the Earth right there. And so the distance that it's going to travel is simply the distance around the Sun, which is just going to be the circumference of a circle, right? Because we know the radius. And so if all we want to know is this distance over here, it's just going to be the circumference, which is just 2 pi r. Right? 2 pi times the radius gives you circumference. And then we're just going to divide that by time, which we're given is 365 days. But to put this in something that we can relate to, let's change this over to meters per second. So let's just convert this bottom. So 2 pi r, 365 days, and there is 1 day, has 24 hours. And then in 1 hour, there are 3,600 seconds. Okay, so this whole thing comes out to you, and r is equal to 1.5 times 10 to the negative 11th meters. When you put this all in your calculator, that comes out to 3 times 10 to the 4th meters per second. Okay, so this thing is traveling around at 3 times 10 to the 4th meters per second. And now keep in mind that this is the velocity. This isn't the angular velocity, which we're going to calculate right now. So let's go ahead and do part B. So the angular velocity, all that is how many degrees this thing covers in a certain amount of time. So to find that, all we have to do is, so omega is equal to the amount of degrees it's going to cover, or given how long it's going to take for one time to go around, right? It was 365 days. So the amount of radians it covers from here all the way around and back to here is just 2 pi, right? So omega is equal to 2 pi over the amount of time, which is 365 days. And again, we're just going to put it into radians per second. So let's convert days over seconds. So 24 hours in 1 day. So days cancel. And then there's 1 hour. 3,600 seconds in 1 hour. Okay. So now our hours cancel, and so we're left with just seconds. And so when you do this, this actually comes, put this in your calculator. This comes out to 2 times 10 to the negative 7 radians per second. So that means the Earth covers 2 times 10 to the negative 7 radians per second. So it's not rotating a super large amount, but its speed is really great, right? 3 times 10 to the 4th meters per second. And I just wanted to point out something here as well. You could have just used the other equation for angular velocity, which is W is equal to the tangential velocity over r. So you would just plug in 3 times 10 to the negative 4 meters per second into for the V right here. That's what we calculated up here, right? V. And then we're also given r. So this is just another way to calculate the angular velocity. But they both come out to the exact same thing. Okay, so the next thing we're trying to solve is centripetal acceleration. So we know that the centripetal acceleration is equal to v squared over r. So this is mostly just a plug and play right here. And so let's just plug in our v, which is this one, right? This is our v. So 3 times 10 to the 3 times 10 to the 4th meters per second over r, which is 1.5 times 10 to the 11th. When you put this in a calculator, you get 6 times 10 to the negative 3 meters per second squared. Okay, and that's pretty much it for problem 6.14.